Find the interval of convergence and radius of convergence for the given power series. We have the sum from n equals 1 to infinity of the product of negative 1 to the power of n and x to the power of n and the quantity n plus 9, all divided by 3 to the power of n. To begin, because of the x to the nth, which we can think of as the nth power of x minus 0, the power series is centered at x equals 0. Using the form shown here on the right, this indicates c equals 0. And now to begin, we'll apply the ratio test, which means we need to determine the limit as n approaches infinity of the absolute value of the quotient of a sub n plus 1 and a sub n, which means we'll have the limit as n approaches infinity of the absolute value of a sub n plus 1, which is negative 1 to the power of n plus 1, times x to the power of n plus 1, times quantity n plus 1 plus 9, or n plus 10, all divided by 3 to the power of n plus 1. And then instead of dividing by a sub n, we'll multiply by the reciprocal of a sub n, which indicates we have times 3 to the power of n divided by the product of negative 1 to the power of n, x to the power of n, and the quantity n plus 9. And now let's begin to simplify. Negative 1 to the power of n plus 1 divided by negative 1 to the power of n simplifies to one factor of negative 1 in the numerator, which isn't really going to matter because of the absolute value. X to the power of n plus 1 divided by x to the power of n simplifies to one factor of x in the numerator. And 3 to the power of n divided by 3 to the power of n plus 1 simplifies to one factor of 3 in the denominator. Let's now write this as the limit as n approaches infinity of the absolute value of, again, we can leave off the negative 1 because of the absolute value. Let's write x divided by 3 as 1/3 x. Then we have times the quantity n plus 10 divided by the quantity n plus 9. In this form, we can determine the limit as n approaches infinity because n plus 10 is degree 1, and so is n plus 9. The limit equals the ratio of the leading coefficients, which is 1 divided by 1, or 1. So this quotient approaches 1, and therefore the limit is equal to 1/3 times the absolute value of x. And because we're applying the ratio test, in order for the power series to converge, this limit must be less than 1, which gives us the inequality 1/3 times the absolute value of x is less than 1. Solving for the absolute value of x, we multiply both sides by 3, which gives us the absolute value of x is less than 3. Again, because we have x inside the absolute value, we know the power series is centered at x equals 0, and because the absolute value of x must be less than 3, remember we can think of the absolute value of x as a distance from 0. The distance from 0 must be less than 3, which indicates the radius of convergence equals 3. Let's record this below. And again, because the power series is centered at 0, we now know the power series is convergent on the open interval from 0 minus r to 0 plus r, which gives us the open interval from negative 3 to 3. This may or may not be the interval of convergence. We still have to test whether the power series converges or diverges at the endpoints. But we do know the interval will start at negative 3 and end at positive 3. Let's check the endpoint on the next slide. Let's first test x equals negative 3, which gives us the power series, the sum from n equals 1 to infinity of negative 1 to the power of n times negative 3 to the power of n times the quantity n plus 9, all divided by 3 to the power of n. We can write the nth power of negative 3 as negative 1 to the power of n times 3 to the power of n, giving us the sum from n equals 1 to infinity of negative 1 to the power of n times negative 1 to the power of n times 3 to the power of n times the quantity n plus 9, all divided by 3 to the power of n. Simplifying, 3 to the power of n divided by itself simplifies to 1. Negative 1 to the power of n times negative 1 to the power of n is negative 1 to the power of 2n, which means the exponent will always be even, and therefore the result will always be positive 1. So these simplify to 1, which means we now have the sum from n equals 1 to infinity of just n plus 9. which you should recognize is going to fail the nth term divergence test, which is that the limit as n approaches infinity of a sub n, which in our case is n plus 9, doesn't equal 0, then the series diverges, in this case at x equals negative 3. And this limit is approaching infinity, which doesn't exist. More importantly, isn't 0, and therefore the series diverges at x equals negative 3 from the nth term divergence test. So we do not include negative 3 in the interval of convergence. The interval is open on negative 3. And now we test x equals positive 3. When x equals positive 3, we have the sum from n equals 1 to infinity of negative 1 to the power of n times 3 to the power of n times the quantity n plus 9, all divided by 3 to the power of n. Again, simplifying, 3 to the power of n divided by itself simplifies to 1. Notice we have the alternating series given by the sum from n equals 1 to infinity of negative 1 to the power of n times the quantity n plus 9. Let's apply the nth term divergence test. This limit does not exist, and we should recognize this because the limit as n approaches infinity of n plus 9 approaches infinity. The only difference with this limit is the negative 1 to the power of n, which oscillates the sign. These values oscillate between values approaching positive and negative infinity, and therefore the limit doesn't exist. And the series diverges at x equals 3. Again, due to the nth term divergence test. So once again, we do not include 3 in the interval of convergence. The interval of convergence is the open interval from negative 3 to positive 3, meaning the endpoints are not included in the interval. I hope you found this helpful.